Okay, this is section 4.6, and this is on optimization. And so here's something that comes from the book and just some strategies. Number one, read the problem. And it says read it till you understand. You need to know what's given and what unknown are you trying to optimize. Number two, often you need to draw a picture. Label any part that could be important to the problem. Then figure out the variables and the relationships. Identify the unknown variable. Then you're going to write an equation for the unknown. If you can, express it as a single variable or in two equations that have two unknowns. And you have to work at that sometimes. Then you're going to test the critical points and the endpoints in the domain of the unknown. And use what you know about the shape of the graph. Use the first and second derivatives to identify and classify functions' critical points. All right, so here's the deal. Let's practice this and see what we're talking about. Sometimes you'll have two equations. The main equation is the one you want to optimize, either finding a max or a min. The second equation might be to write the main one in terms of one variable. So let's look at an example. All right, an open top box is to be made by cutting small congruent squares from the corners of a 12 by 12 sheet of tin and then bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? So here's the drawing that you're given. You don't have this little inside part here. I drew that in. We know that outside we have 12 and we have 12 here. Now I drew, actually you didn't even have this because I can tell that I drew that with the drawing tool, and it's 12 by 12, so it doesn't even at all look drawn to scale. It should be a square. Sorry. Anyway, you get the idea that you are going to take out corners and then you're going to be folding up the pieces to actually make a box that looks like this. So if you have 12 here and 12 here, you're going to cut out an X, an X, an X, and an X. Why do I have the domain as X has to be between 0 and 6? Well, if I'm taking out an X here and an X here, if I have two X's and each one were equal to 6, I would be taking out 12 and I would have nothing left. So that makes sense that it has to be less than 6. Okay? So think about the dimensions of what is left. What is left? On this end, you have 12 and you take away 2x. On this side, same thing, 12 minus 2x. And the x becomes the height of the box. So I've drawn in my dimensions there. All right, so we want to make the box hold as much as possible. That tells me we're looking to work with volume. So our main equation would be volume equals length times width times height. Well, I need to put these all in terms of one variable. So I could say my length is 12 minus 2x, my width is 12 minus 2x, and my height is x. All right, then you've got your equation in terms of x. You're going to multiply those all out. You're just going to do that algebraically, and you get this v. Then you're going to take the derivative, and you get 144 minus 96x plus 12x squared. You want to set that equal to 0 and solve it. So when you solve it, it factors nicely, but you get x is 6 and x is 2. Well, 6 is not in the domain. Remember, we found that up here that x had to be between 0 and 6. It's a badly made 6. All right, so we can discard it, and we can assume that x is going to be our critical point. And f of 2, when we plug that into the original here, this one is our original, 144x minus 40, blah, blah, blah. So you would get 128. Now we do have to evaluate the endpoints of our domain. So 0 there and 6 gives us 0. So this 2 gave us the maximum value. So the boxes should be done with 2-inch squares. Okay, so that's what we're going to do. We know how to take the derivatives. We know how to set it equal to 0 and solve that and find the max and min. It's really just setting it up that we're going to have to worry about. Okay. All right, consider the parabolic arch, that's this guy, whose shape may be represented by y equals 169 minus x squared. So this is 169 minus x squared. And everywhere on this shape, that's the value of y, okay? Where the base lies on the axis from x equals negative 13 to x equals 13. Find the dimensions of the rectangular window that's going to give you the maximum area, okay? All right, so what's the area of a rectangle? LW, okay? And so that's going to be 2 of these x's, because this is an x and that's equal. So this is an x value and this is an x value, and it's got to be the same, okay? And so we could also say that a equals 2x times y, right? Because here's the height, and that's a y value. So 2x, y. But what was y? Y was equal to 169 minus x squared. So I can now say that a is equal to 2x times 169 minus x squared. And then I'll multiply that out. A prime then is 338 minus 6x squared. Whoops. So I'm going to set that equal to 0. So 338 equals 6x squared. And you could get 56.3 equals x squared, which is about 7.5 x. And so the width would be 2 of those, be 15. And then y equals 169 minus x squared. So y equals 169 minus 56.25, I guess, actually. And so the height would be then 112.75. The thing is, that would be fine for me, but for MATLAB, it's expecting you not to be doing decimals. It wants radicals if need be. And so what we would have here, let's talk about MATLAB over here. Okay, so you would have 338 over 6 equals x squared, okay? And so we could actually reduce that a little bit and get 169 over 3 is x squared. That's a perfect square, so we'd have 13 over the square root of 3 equals x. And when you rationalize that, I've run out of room. When you rationalize that, you get 13 square roots of 3 over 3 is x. And so the width is 2 of those. 2 times that equals 26 square roots of 3 over 3. So that would be the width. And then y equals 169 minus 169 over 3, because that was x squared. And so then you would turn that in, you'd get a common denominator, and you'd have 507 minus 169 over 3, which is 338 over 8. Is that right? Why do I have that? Hold on. Sorry, I don't know why I wrote 8. That's a 3. So, in MATLAB, those are the answers you're going to want. Okay? Okay, rectangular plot of farmland will be bounded on one side by a river and the other side by a single-strand electric fence. With 800 meters of wire at your disposal, what's the largest area you can enclose and what are the dimensions? Okay, do you like the You like the picture? So I have the river and I have the fence and it's electrified. Awesome. Okay, so if you start with 800, okay, you've used up x, so this piece is what you have left, so that'll be 800 minus 2x. So let's think about what we could know. Perimeter is going to equal x plus 800 minus 2x, and area is going to be x times 800 minus 2x. And we are trying to maximize area. So let's go ahead and do this. A equals 800x minus 2x squared. A prime is 800 minus 4x. So let's set that equal to 0. 800 minus 4x equals 0. Negative 4x equals negative 800. X equals 200. So that's the shorter side. And 800 minus 2x will be 400, which is the longer side. And the area is 400 times 200. We've got, there's one side, that's that. And so we would have 80,000. So I think that's everything it asked for. Let's look. Maximum area, so that'll be the 80,000, and the shorter was 200, and the longer was 400. Okay? All right. On this one, you are designing a rectangular poster that's going to contain 48 inches of printing with a 3-inch margin at the top and bottom and a 1-inch margin at each side. What overall dimensions will minimize the amount of paper used? And so h equals and width equals. So we don't know what these are. Let's start out and say that A could be x, y, x times y. All right. We do know the area of the poster. It's going to contain 48 inches of printing. So if we said 48 equals, so this is this. So if we could, we got a 3-inch margin here and a 3-inch margin here. We've got one here and one here. And so this area inside here is 48. So on the X part, we're taking away 2. We're taking away 1 and 1, that's 2. And the Y part, what are we taking away? 6. Okay, so we got 48 equals, here, let's solve this way. We can't multiply that or anything. Let's go ahead and divide this guy over here. And then let's add the 6 over. So we got 48 over x minus 2 plus 6 equals y. Okay? All right. So we've written y in terms of x. Now let's do the area. Okay, before we do the area, let's go ahead and get this all as one fraction. So if I want this to be over x minus 2, change 6 over 1 into something with that as the denominator, I'm going to have 6x minus 12 up here. So this is 48 plus 6x minus 12 all over x minus 2. That equals y. Now I'm going to substitute that y right here for my area. So a equals x times 48 plus 6x minus 12 all over x minus 2. Okay, so I can clean that up a little bit. there's an x on the outside. So I'll go ahead and multiply that x now. A equals 36x plus 6x squared over x minus 2. Okay, so now to take the derivative of that, I've got to use the quotient rule. So a prime is x minus 2 times 36 plus 12x minus 36x plus 6x squared times 1. So that's all that, over x minus 2 squared. Okay, so I got to clean this stuff up on the top. I'm going to have 12x squared plus 12x minus, you're not going to call that. Let me make this, okay. So we've got 36x minus 72 plus 12x squared minus 24x minus 36x minus 6x squared, all over x minus 2 squared. Let's clean that up. So we've got 6x squared, we've got 36 minus 36, so we have minus 24x, and then we've got a minus 72. Okay? Alright, so that's what a prime is. And the only thing you might do is factor out a 6 over there. Okay? Alright, so if I set that equal to 0, so I've got that equal to 0. This is going to go away over here. If you multiply it, the 6 will divide and be gone. So now you've just got this. I don't need that. So that factors. Get rid of this. Okay, so we have x minus 6 and x plus 2 equals 0. So x is 6 or x is negative 2. We're talking about dimensions here, so that x minus 2, that's x equals negative 2 is going to get discarded, and we have x equals 6. And then the y value is going to be 48 over 6 minus 2 plus 6. So y equals 12 plus 6, which is 18. So let's see, what did it ask for? Whoops. Wanted to know the height and the width. And so we've got 6 and 18. Okay. Okay. So that'll get you on that one.